1.1 says the impulse delivered by a net force acting on an object is equals to the. So let's talk about impulse. We know fully well that impulse is the change in momentum, right? So the question is saying the impulse delivered by a net force acting on the object will be equals to what? A says the initial momentum of the object, B says the final, C says the change in the momentum of the object. We don't have to go any further. We know that the answer is C, right? Impulse is the change in the momentum of an object. And then D says the rate of change in momentum of the object. That is the net force itself, right? The rate of the change in the momentum. Here we're only interested in the impulse, which is the change in the momentum of an object. And 1.2 says the graph below represents the relationship between the net force exerted on an object and the displacement it undergoes, right? The net force and the displacement are in the same direction. And then we have a graph there. And then which one of the following statements can be deduced from the graph? A says the area between the graph and the displacement axis represents the net work done by the force. Let's look at it and see if it's true, right? We know that work is equals to force multiplied by the displacement and cos of the angle between the direction of the displacement and the force that is acting. We are told here on this question that the force and the direction are the same, right? They're going in the same direction. So the angle will be 0, and cos of 0 we know that it's 1. So the work done will be equal to the force multiplied by the displacement. The area of this graph will clearly be equals to the force, right, on the y-axis. So we have force and then the displacement on the x-axis, right, which is delta x. Is a rectangle, so the area is length times breadth, right? And this is clearly equals to the work done by the force on that object. So we go in with option A. Let's see if option B, C, D makes any sense. Option B says the area between the graph and the displacement axis represents the power. F multiplied by delta x is not the power, so there's no way that can be true. And then C says the gradient of the graph represents the change in kinetic of the object. That is not true. And then D saying the gradient of the graph represents the work done by the force. It's also not true. So A is definitely our option here, right? We already know. We just disproving all the other options. And then 1.3 says the diagram below shows all the forces acting on an object being pulled to the right by a force F acting at an angle theta to the horizontal. Which of the following expressions can be used to determine the magnitude of the kinetic frictional force acting on the object? This is one of the equations I really like, right? Because most people get them wrong. So we know fully well that the kinetic frictional force will be equals to the coefficient of the friction multiplied by the normal force. Nothing is said here about the coefficient of the static friction, right? So it will just remain as it is. So what we essentially doing in this question, we find in the normal force. Can you find the normal force when the diagram is like this? So physics 101, free body diagram, right? So let's have a free body diagram of all the forces acting on the vertical axis so that we can determine the normal force. So which forces are acting? We know that the normal force is pointing up, and then we know that the weight is going down, right? But then not only is the normal force acting up, there is a force F that is acting at an angle, right? But then, like for us, we can resolve this force F and find the vertical component and the X component. So we're going to have the X component going like that, and then the vertical component going up, right? So now you can see that the normal force plus the vertical component of the applied force is equal to the weight, right? So now the normal force becomes the weight minus the vertical component of the applied force. But then how do we find that vertical component of the applied force? We say the force multiplied by sine of theta, right? And which option is that in our options? So we have the work, so we have the weight minus the force. So that is clearly option B, right? So the answer for 1.3 is definitely B, right? But then what happens if the force is acting down and not acting up? Story for another day. And then 1.4 says the position time graph below represents the motion of a ball from the instant it is released from rest from a certain height above the floor and bounces off the floor a number of times. Ignore the effects of air friction, right? So our ball is released from some height, right? And then we hit the ground. So here we definitely take in down as positive, right? And then it bounces off, reaches maximum height, goes down again, hits the ground, and then goes up, and then it goes down to the ground again. And then the question is saying which point PQRS on the graph represents the position time coordinates of the maximum height reached by the ball after the second bounce, right? So here, this is where it's released, and then it hits the ground and bounces off for the first time, right? And then maximum height goes down again, hits the ground and bounces off for the second time, right? So the maximum height reached after the second bounce is at point S, right? And that is option D. So for 1.4, our answer is D, right? If the question was saying after the first bounce, then our answer would be Q, which is option B. But then here we are interested on the second bounce, which is option S, right? And then that is D on our multiple choice. And then 1.5 is saying the kinetic energy of a car moving at velocity V is K, right? The velocity of the car changes to 2V. What is the new kinetic energy of the car? So here I usually advise people to give these variables values, right? Because if you work in variables, most people can't do it. But I can, and I'm going to show you how. So for the first instance, we have our velocity being equals to V, right? And then if we calculate the kinetic energy there, we're going to get 1 over 2 the mass V squared, right? But then now the velocity has changed, and then it's now 2V. So what will be the kinetic energy? 1 over 2 m, and in place of V, now we don't have V anymore, but we have 2V, right? So we have 2V squared. So we're gonna get a half the mass. What is 2V squared? 2 squared is 4, right? And then a V squared is V squared. So now we have a half multiplied by 4. So we're going to get 2mv squared, right? So from a half mv squared to 2mv squared, right? How is the kinetic energy of the new car different from the first car, right? It's 4 times greater, because you can easily say 2mv squared divided by a half mv squared. This should be equals to 4. mv squared and mv squared cancel out. We have 2 divided by half, which is equals to 4. So the kinetic energy is 4 times greater, right? And that is option D. And then now let's do 1.6. 1.6 says that a sound source approaches a stationary observer at constant velocity. Which one of the following describes how the observed frequency and the wavelength differ from that of the source? Before we even look at the options, let's look at the concepts first. We know fully well that if a sound source is moving, it's approaching a stationary listener, right? Then the listener will experience a higher frequency, right? And then what is the consequence of a higher frequency? The consequence of a higher frequency is less wavelength, because they are inversely proportional to each other. So we're looking for an option that says higher frequency and less wavelength, right? Option A says the observed wavelength will be greater than. So that cannot be true. We know that it's supposed to be less than, right? And then B says the observed frequency is less than, so that is true. And then it also says the frequency is less than. That is wrong, right? C says the observed wavelength is less than, and the observed frequency is greater than. And that's exactly what we're saying, right? So for 1.6, we can go with C. And then 1.7 says the electric field pattern between two charged spheres A and B is shown below, right? We have the electric field pointing towards A and moving out of B, right? So before we go any further, if the electric field lines are pointing towards, then that sphere is negatively charged. And then if the electric field lines are pointing outwards, then that sphere is positively charged, right? Which one of the following statements regarding the charge of spheres A and B is correct? Sphere A is negatively charged, right? We know fully well that that is true. And then sphere B is positively charged. Yeah, that is true because the electric field lines are radiating outwards, right? So before we go any further here, our answer for 1.7 is A. And then 1.8 says the SI unit of the rate of flow of charge in a conductor is. So yeah, back to the concepts. The rate of flow of charge. What is the rate of flow of charge? We know that I is equals to Q divided by delta T, right? So current is the rate of flow of charge. And what is the SI unit of current? Ampere, right? And then which option is that? It's clearly option C, right? So 1.8, our answer is C. Yeah, it's pretty much easy, not so complicated. And then 1.9 is saying which one of the following changes to the design of an AC generator will increase its maximum EMF output. This is actually a grade 11 work, right? When you're talking about electromagnetism, you know that if you want to increase the maximum EMF, then you have to increase the number of turns on the coil, right? And then for 1.9, that is clearly option D. Another way you can increase the strength of the magnets, right? Not change the polarity, but increase the strength of the magnets. There's other ways too, but stories. 1.10 says a line emission spectrum is formed when, okay, back to the basics again. So emission spectrum, right? So an emission spectrum is formed when we go from higher energy levels to lower energy levels, right? And then an absorption spectrum is formed when we go from lower energy levels to higher, right? Here we're talking about a line emission spectrum, right? So we're looking for higher to lower. Option A says electrons in the ground state moves to a higher energy state. No, that's absorption, right? Lower to higher. Now we want higher to lower. And then B says electrons in the higher energy state move to a lower state. We don't have to go any further. That's what we're looking for. So we have two blocks here. One of mass 2 kg and the other one of mass 5 kg. And then there's a force applied on the 5 kg block at an angle of 20 degrees. And then we are told that the 2 kg and the 5 kg blocks, they both experience kinetic frictional forces, right, of 10 Newton and 15 Newton respectively, right? So the 2 kg block experiences a kinetic frictional force of 10 Newtons, and then the 5 kg a kinetic frictional force of 15 Newton. That's what respectively is basically telling us. And then the first question, 2.1.1, it says, let's state Newton's second law of motion. Again, Newton's second law of motion in words, it just states that when a non-zero resulting force is applied on an object, the object will accelerate in the direction of the non-zero resulting force with an acceleration directly proportional to the F net and inversely proportional to the mass. right? So we know fully well that F net is equals to ma. And then in this equation, if you make acceleration the subject of the formula, you basically get the definition, right? Acceleration will be equals to F net divided by the mass. Clearly in this case, the acceleration is directly proportional to the F net and inversely proportional to the mass, right? And then 2.1.2 says, let's draw a labeled free body diagram for the 5 kg block. So here's our 5 kg block here, right? So free body diagram, we denote the body with a dot, right? So there we have our dot. We are told that there's a force applied, right, at an angle of 20 degrees relative to the horizontal. So let's have that force that is applied, right? So we have FA, A denoting applied. And then no questions asked. Any object on Earth will always experience FG, right? The force of gravity. So we have Fg. And then if that body rests on a surface, then the surface will exert a normal force on the body, right? So there we go, normal force. And then apart from the normal force, the 2 kg and the 5 kg block are connected by a string, right? So we must have tension, right? So we have tension there. We are also told that there's a kinetic frictional force acting on the blocks, right? So we can have Fr also acting to the left. So let's, do 2.1.3, which says that let's calculate the magnitude of force F. Force F is the applied force, right? That must be applied at an angle of 20 degrees to the horizontal to make the 2 blocks accelerate at 2 meters per second to the right. So in this situation, we need the acceleration to be equals to 2 meters per second. So here, we're trying to find the magnitude of force F that must be applied at an angle 20 degrees to the horizontal, right? So the force F that is applied, it's applied on the 5 kg block. So we're going to go to the 5 kg block and try see if we can get the magnitude of force F. So what are we essentially saying? We're saying that for the 5 kg block, right, F net is equals to ma, right? So now in place of F net, we can add the forces that are acting, and in place of ma, we have the mass and we know the acceleration. So which forces are acting? We know that along the horizontal, we are going to have Fa x, right? We're going to resolve the force applied along the x, right? And then now we're going to minus all the forces that are opposing the motion. Which forces are opposing the motion? Obviously, frictional force will be opposing the motion, and then the tension force will also be opposing the motion. And this will all be equals to ma. So what is Fax? Fax will be the force applied multiplied by cos of 20 degrees. We know fully well that if you wanna find the x component, you take cos of the angle, and then if you want to find the y component, you take sine of the angle, assuming that you are on a flat surface, right? And then minus frictional force. The frictional force, it is said to be equals to 15 Newton, right? So minus 15 and then minus the tension. We don't know what the tension is, so we're just gonna leave it like that for the moment. And then that is all equals to ma, right? We know the mass fully well. The mass is 5 and the acceleration, we're assuming that it is 2, right? The equation says, let's find the magnitude of the force F that must be applied if the blocks will accelerate at 2 meters per second. So now, let's go ahead and solve for Fa cos of 20 degrees, right? So we have Fa cos of 20 degrees being equals to, so we're taking minus 15 to the right hand side and minus tension, right? But then on the right hand side, we have 5 multiplied by 2, which is just 10. So we're going to have 10 plus 15 plus tension, right? So now we can divide both sides by cos of 20. So we're going to get force applied being equals to 25 plus the tension divided by cos of 20. So it's easy to see now that we just need the tension. If we get the tension, then we basically have the force applied, right? So we have already used the 5 kg block. What we can do now is to use the 2 kg block and see if we can get the tension from the 2 kg block. So from the 2 kg block, there is the tension that is pulling it to the right and the frictional force that is pulling it to the left, right? So we're gonna have something of this manner. So we have 2 kg, and then in place of 2 kg, we know fully well that F net is always equals to ma. So now the force that is greater than the other is the tension, and then we're going to subtract the force that is opposing, which is the frictional force, and this will be equals to ma. But we know fully well what the frictional force is, right? It's given to us. It is said to be equals to 10 Newton, right? So we have frictional, which is 10 Newton. The mass is 2 kgs, the acceleration is 2. So the tension is basically equals to 4 plus 10, which is equals to 14 newtons, right? So here in place of T, we can substitute 14 newtons. So we're going to have 25 plus 14 divided by cos of 20 degrees. And if you put that in your calculator, you're going to get the force applied being equals to 41.50 newtons, right? And we basically done with that equation. Let's move to 2.2. 2.2 is into us. The Earth exerts a force of 1,842.5 newtons to keep a satellite of mass 200 kg in orbit around the Earth, as shown in the diagram below. We have a very fancy sketch there. And then the question says, let's calculate the distance above the Earth's surface at which the satellite orbits the Earth. So let's look at the information we have, right? We have the force that is acting between the Earth and the satellite. And then we have the mass of the satellite, right? Apart from the mass of the satellite, we have the mass of the Earth, because the mass of the Earth is a constant, right? So we have the mass of the Earth. And then now, what we're looking for is the distance between the Earth and the satellite, right? So we can use Newton's law of gravitational acceleration, right? Every body attracts every other body with a force that is directly proportional to their masses and inversely proportional to the square distance between them, right? So we're saying that F is equals to G, that G being a constant, right? And then mass of the satellite, mass of the Earth, and then divided by the distance between them. The distance between them will be equals to the radius of the Earth plus the actual distance between the Earth and the satellite, right? So we're saying that F is given to us, right? 1,842. So we have 1,842.5 being equals to that capital letter G, right? Which is a constant. It's 6.67 times 10 to the minus 11. So now the mass of the satellite is said to be 200 kgs. And then the mass of the Earth, right? 5.98 times 10 to the minus 24 divided by the distance between them, right? So we have distance squared, right? So now we're solving for the distance squared. It's easy to see. We know fully well that if we have A is equals to B divided by X, and you want to find X, you're going to cross multiply, right? You're going to get AX is equals to B multiplied by 1. So X will be equals to B divided by A, right? So we're going to apply the same idea in this situation. Our X is D squared, right? So we're going to have something like this. So we're going to have D squared being equals to this entire expression here, right? So let me just duplicate it for the sake of time, and then we dividing that by 1842.5. And then after you do that, you definitely take square roots on both sides, right? So you take a square root on this side, and then you take a square root on the right hand side too, and then you're gonna get a distance of 6,579,982.8 meters, right? So this is the distance between the Earth and our satellite. But then we don't want the distance between the Earth and the satellite. We want the distance above the Earth's surface at which the satellite orbits, right? Even if you look in the question here, it's in bold, right? The distance above the Earth's surface. So that distance will be equals to the distance we just calculated right now minus the radius of the Earth. This question has 5 marks, right? So if you stop here, you only have 3 marks. The other 2 marks is for you to subtract the Earth's radius from this value that we have. So if we do that, we can now say the distance above will be equals to 6,529,982.8 meters minus the radius of the Earth, right? The radius of the Earth is a constant, so we know fully well that that is 6.38 times 10 to the 6 meters, right? So your answer is going to be equals to 1.9998 times 10 to the 5 meters. So what we have below is a velocity time graph that shows the motion of a ball thrown vertically downwards, right, from the top of a building and bouncing off the floor as it hits the ground. And then we can ignore the effects of air friction, and then it's a must that we take upward as positive. And then the first question, 3.1.1, says using equations of motion only, let's calculate the height from which the ball is thrown, right? So we are looking for delta y, the height at which the ball is thrown. Problem solving 101. We'll look at the information we have, right? And try use that information to find out what we don't have, right? So what information do we have here? At t is equals to 0, we have a velocity here of which the ball is thrown at, right? So the velocity that we have here, which will be our VI, right, is given as minus 20 meters per second. And then when the ball hits the ground, it has a velocity of minus 25 meters per second, right? So we can say our VF in this instance would be minus 25 meters per second, right? We know acceleration. We always know it's a constant, right? If we're taking upward as positive, then our acceleration should be minus 9.8 meters per second squared. So we have VI, we have VF, we have our acceleration, and we'll need delta y, right? So which equation of motion has these 4 variables that we can use? We know fully well that that equation is VF squared is equals to VI squared plus 2a delta y. We have the acceleration, we have VI, we have VF. We're looking for delta y, right? So what is VF? VF is minus 25, right? That's the velocity at which our object strikes the ground. And then VI is minus 20, the velocity at which it is thrown off the building, right? Plus 2 multiplied by A. A is our gravitational acceleration, minus 9.8, right? And then we're looking for delta y. So basically, the physics is done now. We are just solving the math. So we're going to have minus 25 squared minus 20 squared being equals to 2 multiplied by minus 9.8 delta y. We just took minus 20 squared to the left hand side, right? So now it will be obvious what we're going to do. We're going to divide both sides by 2 multiplied by minus 9.8. So if we do that, we're going to get delta y being equals to minus 25 squared minus 20 squared, everything divided by 2 multiplied by minus 9.8, and then our delta y is equals to minus 11.48, right? Which is just 11.48 meters. So the height above the ground is 11.48 meters. Now we can do 3.1.2. 3.1.2 says let's find the time t on the graph. So time t on the graph is here, right? So let's analyze our motion. Here at this point, the object is thrown downwards, right? And then at minus 25, it hits the ground. When it hits the ground, it bounces off with a velocity of 12 meters per second, right? Until it reaches its maximum height. So what we do here, we calculate the time for this part of the motion from the moment it is thrown downwards to the moment it hits the ground. And after we're done with that, we calculate the time from the moment it leaves the ground to the maximum height which it reaches, right, when its velocity is equals to 0. So for that part of the motion, we have Vf, obviously, right? And then we have Vi, we have A, but then now we don't need delta y. We already have it. We're looking for delta t, right? We want that time, because that time, delta t in our graph here, is the time from the instance the ball or the object is thrown downwards, right? So here for that first part of the motion, we're gonna get Vf is equals to Vi plus A multiplied by delta t. What is Vf? Minus 25. And what is Vi? Minus 20. We know fully well what our acceleration is, minus 9.8, and then multiplied by delta t. So we're gonna have minus 25 minus 20 being equals to minus 9.8 multiplied by delta t. So we divide both sides by 9.8, right? If you do that, you get delta t being equals to 0.5102 second, right? And then we are done with that part of the motion. Now we need the part of the motion from the time it leaves the ground to the time it reaches its maximum height, right? So what do we have there? We have Vi for that part of the motion, and then we have Vf, right? Maximum height. We know the velocity is equals to 0, and then we have the acceleration, and we're looking for the time. So what is Vf in that instance? We're still using the same formula. Vf is equals to Vi plus A delta t. So Vf is 0, right? Maximum height, and then Vi will be 12. Here it is, right? 12 meters per second, and it's positive because the object has left the ground. It is now moving up, plus the acceleration, which is minus 9.8 multiplied by delta t. So you can see what we're gonna do here. We're gonna take 12 to the left hand side and divide both sides by 9.8. So delta t is going to be equals to minus 12 divided by minus 9.8, right? And that will be equals to 1.2245 seconds, right? So now that time on our graph will be equals to the time from here to here, right? Which is 0.51, and the time from here to here, which is 1.2245. So we add in the two, we have 0.51 plus 1.2245, right? And that should be equals to 1.7345 3.1.45 seconds. 3.1.3, which says that let's determine using equations of motion the magnitude of the displacement of the ball from the moment it is thrown until time t. So the ball is at some height, right? And then it is thrown downwards and then it hits the ground. After it hits the ground, obviously it's gonna move up, right? And then it moves up to some maximum height. At the maximum height, that's our time t. At this instance, we know the height the ball was thrown above the ground, but we're looking for the displacement of the ball, the change in position from the time it is thrown until it reaches maximum height. This is the object's maximum height after it bounces off the ground, right? So we're basically looking for this part here. This is the part we're looking for. So if we find this height from the ground to its maximum height, then we're going to be able to calculate that displacement that we are looking for. So what are we saying? We know the height, right? We know fully well that the height is at 11.48 meters above the ground, right? Now let's find the maximum height it reaches after the bounce, right? So we know fully well that the VI that it leaves the ground with is 12 meters per second, and then the VF, because it's at maximum height, it's 0, right? And then we know the acceleration, but now we're looking for delta y and not delta t. So which equation of motion can we use? We're going to use VF squared is equals to VI squared plus 2a delta y. So VF squared, we have 0 squared, which is equals to VI squared. So that's 12 squared plus 2 multiplied by minus 9.8 delta y. It should be obvious. We're going to take 12 squared to the left hand side and divide both sides by this coefficient here. If we do that, we're going to get delta y being equals to minus 12 squared divided by 2 multiplied by 9.8. This here is supposed to be a minus, and then the answer we get in is 7.346 meters, right? So now our displacement will be equals to 11.48 minus 7.3469, which is equals to 4.1331 meters, right? Now we can move to 3.2. So 3.2 says, can you sketch a position versus time graph for the motion of the ball from the moment it is thrown until it reaches its maximum height from the bounce? Use the ground as the 0 position, right? And then we must indicate the height of which the ball is thrown and the time t, right? Which is things we have calculated. So let me just sketch our Cartesian plane. So on the x-axis we have the time in second. So on the y-axis we need delta y in meters, right? So let's start by indicating the maximum height which it is thrown, right? So the maximum height we say is 11.48. Yeah, like we've been saying, we're moving from maximum height and then it is thrown downwards, right? And then it hits the ground, and then it bounces until it reaches its new maximum height, right? This height here, we know fully well what it is, 7.3469, and then the time here, which is the time t that we're supposed to indicate, we just calculated it not long ago, right? 1.73 second. The diagram below shows trolley A of mass 2 kg traveling at a velocity of v meters per second east on a straight horizontal surface, colliding head-on with trolley B of mass 4 kg traveling at a velocity of 5 meters per second west. And then after the collision, the two trolleys stick together and move at a constant velocity of 1.67 meters per second west. The collision only lasted for 0.01 second. ignore the effects of friction. And then 4.1 says, state the principle of conservation of linear momentum in words. We know fully well that it says that the total linear momentum in an isolated system is conserved. The total linear momentum in an isolated system is conserved. What does that mean? The sum of the momentum before a collision will be equals to the sum of the momentum after the collision. And then 4.2 says, let's calculate the magnitude of the velocity v of the trolley A before it collided with trolley B. The magnitude of the velocity of trolley A before it collided with trolley B. In 4.1, we stated the principle of conservation of linear momentum in words. And then in 4.2.1, we're going to use that definition to determine the velocity v of trolley A. So what does the definition essentially say? We've went through that, right? We're saying that the sum of the momentum before will be equals to the sum of the momentum after. Before the collision, we have the 2 kg trolley moving towards the east and the 4 kg trolley moving towards the west. So what we can do here, we can take one direction as positive, right? It only makes sense to take east as positive. Let's not forget that momentum is given by the momentum is equals to the mass multiplied by the velocity, right? So the momentum of the 2 kg trolley will be the mass of the 2 kg trolley multiplied by the velocity v, right? Plus the momentum of the 4 kg trolley. It will be the mass of that trolley multiplied by the velocity it possesses, right? And this will be equals to, we are told that after the collision they move together, right? They become one body, so we can add up the masses. So we have the mass of A plus the mass of B multiplied by VF that they move with together, right? So what is the mass of trolley A? The mass of trolley A is 2 kg. And then what is the velocity of trolley A before the collision? That's what we don't know, and we're looking for it, right? So we just have V plus the mass of trolley B, which is 4 kg. And then what is the velocity of that trolley? Is 5 meters per second, right? To the west, we must put a negative sign, right? And then this will be equals to, we're summing up their masses. So we have 2 kgs plus 4 kgs. And the velocity after, which velocity do they move with? 1.67 meters to the west, right? So if it's to the west, then we must put a negative sign, minus 1.67, right? And then now the physics is essentially done, and we're just solving the math, right? We're looking for V. So 2 multiplied by V, that will be 2V, and then 4 multiplied by minus 5, that will be minus 20, and that will be equals to essentially 6 multiplied by minus 1.67, which is equals to minus 10.02. So now 2V will be equals to minus 10.02 plus 20, right? So V will be equals to minus 10.02 plus 20, everything divided by 2. And the answer is 4.99 meters per second. We know that positive is to the east, right? So we can write here and say to the east. If the value was negative, then we would know that that velocity is to the left. And now we can do 4.2.2. 4.2.2 says, let's calculate the force that trolley B exerts on trolley A, right? The force that B exerts on trolley A. Since this question is on momentum and impulse, let's use Newton's second law in terms of momentum, right? We know fully well that it says that F net is equals to the rate of change in momentum. So if we can calculate the rate of change in momentum of trolley A, then we will know the force that B exerts on A. So what is the change? We know that delta P is equals to momentum final minus momentum initial, right? So F of B on A will be equals to the change in the momentum of our trolley A, right? So the change in momentum, we're gonna have the mass, which is 2 kg, right? Multiplied by the velocity final. The velocity final is this 1.67 meters per second that they move with after they've joined each other, right? So we're gonna have, and that velocity is to the left, so let's put a minus sign when you substitute it, because we take in east as positive, right? So we're gonna have minus 1.67, and then minus the momentum initial, right? So we have 2 kg again multiplied by the velocity initial. We just calculated it here, right? Is 4.99. So we have multiplied by 4.99, and then we divide everything by the time the collision takes, right? The collision lasted for 0.01 second. So everything divided by 0.01. And then the answer I'm getting here is minus 1,332 newtons. We've already established that the direction to the east is positive, right? So since we have a negative value, then we know that that force is exerted to the west, right? So we're gonna have 1,332 newtons to the west, right? And it makes sense. If trolley B is moving to the west and then trolley A is moving to the east, then when they collide, trolley B will exert a force on trolley A to the west. A force of 62.5 Newton is applied to a trolley of mass m kg parallel to the inclined surface as shown to keep it moving down an inclined surface at a constant velocity. The vertical height of the inclined surface is 12 meters, and then refer to the diagram below. A kinetic frictional force of 35.5 Newton acts on the trolley as it moves down the inclined surface. And then 5.1 says write down the name of the conservative force acting on the trolley. So in our context, in our curriculum, we only have two conservative force that we talk about, right? We talk about gravitational force and electrostatic force. Here in this instance, the only force that is acting on this trolley as it moves down the incline at a constant velocity is gravitational force, right? Gravitational force. And we can move to 5.2. 5.2 says, let's calculate the work done by the friction on the trolley, right? So, fine. We are given the frictional force. Here it is here. It is said to be, so we have frictional force, which is equals to 35.5 newtons, right? And then, apart from frictional force, we know the height, right? But then from the height, we can find the length of the incline, right? How can we do that? We have the angle here, and then we have the height. We can use trig ratios, right? So what we can do, we can say that sine of theta is equals to y divided by hypotenuse, right? But then in this instance, we know the angle. We know that sine of 30 degrees is equals to our y is our height, right? Which is 12 meters. So we have 12 meters divided by the length of the incline. That's what we ultimately interested in. So we can label that as delta x. So it should become easy to see now that delta x will be equals to 12 divided by sine of 30, and then if we do that, we get 24 meters. So we have the frictional force, we have delta x, and then we have the angle between the frictional force and the direction of the motion. So now we can say that the work done by the frictional force will be equals to that force of friction multiplied by the displacement of the object multiplied by the angle, right? So what is the frictional force? We've already said that the frictional force is 35.5, right? We calculated the displacement, that's 24, and then the angle. All the time, frictional force opposes the motion, right? So the angle should be 180 degrees, right? So we have cos of 180 degrees. And then if you punch that in your calculator, you're going to get minus 852 joules, right? So that is the amount of work the frictional force is doing on the trolley. And then now let's do 5.3. 5.3 says write down the change in kinetic energy when the trolley reaches the bottom of the inclined surface. Let's go back to our statement again. We have constant velocity here, right? We know that the change in the kinetic energy is equals to a half mass Vf squared minus a half mass Vi squared. If we are moving at constant velocity, then Vf squared is equals to Vi squared. So the change in kinetic energy should be equals to 0 joules, right? And then now we can do 5.4. 5.4 says use the work energy theorem to calculate the mass m of the trolley. The work energy theorem to calculate the mass m of the trolley. Here I'm going to use work net is equals to the change in kinetic energy. The other formula you can use, you can say that the work done by non-conservative forces is equals to the change in the potential energy plus the change in the kinetic energy, right? Maybe this is the formula you might want to try out and see if it also works. But then I'm going to use this first formula here, right? So what is the work net? The work net is the sum of all the works done by the individual forces, right? So we have the work done by Fg, and then we have the work done by friction, and we have the work done by the force applied, right? And this is equals to Ek. But we know what Ek is. Ek is 0, right? Apart from Ek, we know the work done by friction. We just calculated it in 5.2, right? So what is the work done by Fg? The force of gravity multiplied by the height, and then cos of the angle, right? Plus the work done by friction. We know that that is minus 852, right? And then plus the work done by the force applied. We know that the force applied is 62.5, right? So we're gonna, let me just write it in the line below. So plus 62.5 multiplied by the displacement, and then cos of the angle, right? And this should be all equals to 0. So let's talk about this work done by gravity first. So there's two ways you can use to find the work done by gravity. You can use the gravity itself, right? And the height. Apart from that, you can find the parallel component of the gravity, and then you can use the displacement, right? The distance from A to B, which is 24 meters. If you also use that, we should get to the same answer, right? But then I'm just gonna use this in this question. So what is Fg? Fg is the mass multiplied by the gravity, right? Which is 9.8, and then the height is there on our sketch. We know that is 12 meters, and then what is the angle? The angle between Fg and the change in the object's position relative to the height, right? That angle is 0, so we have cos of 0, right? Because gravity is pulling the object down, and ultimately along the height the object is going down, right? So that angle is 0, and then minus 852 from gravity, and then now we'll have plus 62.5, and then the displacement we calculated it, we know that is 24, right? 24, and then multiply by cos of 180. Why am I saying cos of 180? Because this force applied is pulling the object up but then the object keeps sliding down at constant velocity, right? So the angle between the force and the direction of the motion is 180, and that will all be equals to 0. So you can see here that the only variable we have that is left is the mass, right? So we have solved the conceptual physics problem. Now we're just solving the math. Before I put anything in the calculator, I'm just gonna take everything that belongs to the right hand side to the right hand side, right? So I'm gonna have the mass multiplied by 9.8 multiplied by 12. Cos of 0 is 1, right? So there's no need to include that. That will be equals to now I'm taking this minus 852 to the right hand side, so it will be positive 852. And then this here, right, we know fully well that cos of 180 will be minus, right? So when I take 65 multiplied by 24 to the right hand side, it should be positive, because cos of 180 is minus. Now we're taking it to the other side, it should be positive, right? So here we're gonna have plus 62.5 multiplied by 24. So now it should be easy to see. We're dividing both sides by the coefficient of m, right, the mass. So we're gonna have the mass being equals to 852 plus 62.5 multiplied by 24 divided by that coefficient 9.8 multiplied by 12. And the mass is apparently 20 kgs. We have a sphere A here of charge minus 5 microcoulombs hanging from a ceiling, right, by means of a light inextensible string. And then 100 millimeters away we have a point charge P. And then the first question, 7.1.1 says, did charge the sphere A lose or gain electrons to acquire a charge of minus 5 microcoulombs, right? So if a sphere was neutral, right, and then now it has a charge of minus 5 microcoulombs, did it gain or did it lose electrons? We know fully well that electrons are negatively charged, right? So if it becomes more negatively charged, then it gained electrons, right? So for 7.1.1, this sphere definitely gained electrons. And then 7.1.2 says, calculate the number of electrons gained or lost by sphere A to acquire a charge of minus 5 microcoulombs. The number of electrons gained or lost, right, is equals to the change in the charge of the sphere divided by the charge of an electron, right? So this change is going to be the charge of the sphere final, which is minus 5 times 10 to the minus 6, right? And then initially our charge was neutral, so we have minus 0 here. And then we can divide all of these by the charge of an electron, right? We know fully well that the charge of an electron is minus 1.6 times 10 to the minus 19. So the answer we get in here will be 3.125 times 10 to the 13 electrons. I feel like I've solved this problem before somewhere. Just can't remember. But then anyway, stories in passing. And then 7.1.3 says, let's calculate the electric field at point P due to charge the sphere A. And then the mark allocation is 5, right? We're waiting for 5 marks, which doesn't make any sense because this question is very simple and straightforward. We don't deserve 5 marks. But then anyway, the examiners make the rules. So we have the electric field being equals to K multiplied by the charge of the sphere divided by the distance squared, right? We know fully well that K is a constant. That is 9 multiplied by 10 to the power of 9. And the charge on our sphere, right, is 5 times 10 to the minus 6. We've already established that the distance is 100 millimeters, right? So that 100 millimeters, to convert it to meters, we divide by 1,000, right? So we're going to have 100 divided by 1000 squared. And then if you punch that in your calculator, you're gonna get 4.5 times 10 to the 6 newtons per coulomb of charge. And just like that, you've earned yourself 5 marks, right? Which is, yeah, unheard of. And then 7.2 so is an identical sphere B. Here it is here, carrying an unknown charge placed on an insulated stand is brought closer to sphere A. Yes, sphere A. And then charged sphere A shrinks to the right and comes to rest so that the string makes an angle of 30 degrees with the vertical. And the tension in the string is 25 newtons. The distance between the two charged spheres is 50 millimeters as shown in the diagram below, right? And then without wasting any time, 7.2, so 7.2.1 says, is the charge on sphere B positive or negative? Give a reason for your answer. So we have sphere B here, right? And then we have sphere A. And then when sphere B is moved closer to sphere A moves further away, right? So they should have like charges, right? That's why they're repelling each other, so to say. So now we can conclude that sphere B has a negative charge, right? Why are we saying it has a negative charge? Even the question says we should give a reason. It has a negative charge because it is repelling sphere A, and sphere A has a negative charge. So sphere B must have a negative charge consequently, right? Yeah. And then 7.2.2 says, so let's calculate the magnitude of the charge on sphere B. Yeah, here that's, where it starts to get a bit complicated. Let's calculate the magnitude of the charge on sphere B. So problem solving 101. Let's look at the information we have, right? So with regards to sphere B, we know the distance r away from sphere A. We know k is a constant, right? We know the charge of sphere A, and then we don't know the charge of sphere B. That's what we're looking for, right? Another thing we don't know is the electrostatic force between A and B, right? If we can find the electrostatic force between A and B, then we can use F is equals to K Q1 Q2 divided by R squared, right? We have R squared already. We have Q1, we don't have Q2, we have K. So if we find F, then we can find the charge on sphere B, right? So how can we possibly find that F? We can use sphere A, right? Here in this question, you don't have any option. You have two spheres, A and B. We have exhausted all our options with regards to sphere B, and we can't find a way to go to the answer. We are definitely going to use sphere A. So sphere A is at rest there, right? If sphere A is at rest, then FB on A should be equals to the tension force, because the electrostatic force of B on A is moving A to the right, and the tension is holding A from moving to the right, and then A is at rest. So these two forces are balanced, right? And then if we can find the x component of the tension, then we can find FB on A, right? So let's see what happens. So FB on A will be equals to the x component of the tension, right? Because clearly the tension is acting at an angle. Let me make it a bit more clear. So we have sphere A here, right? And then FB on A is pushing to the right? And then the tension is acting at an angle. So if we resolve the tension, then we're gonna know the magnitude of FB on A, right? So now we can say that the tension is 25, right? multiplied by, if you want to find the x component, you use cos on a flat surface, right? And then on an inclined, you use sine. And then the angle that you use is not this 30 degrees that we have here. You use the angle between the force and the x component. Since that angle, this angle here is 30, right? This angle here will be 90, and the angle we're supposed to use is this 60 degrees here, right? So now we can say cos of 60 degrees. So we have 25 multiplied by cos of 60. 25 multiplied by cos of 60 is 12.5 newtons, right? So now we know FB on A. We can use this formula here to find the magnitude of charge P. Right? A very interesting problem. So now we can say FB on A is equals to K, the charge of B, the charge of A divided by the distance between them squared, right? So what is FB on A? FB on A, we know fully well that that's 12.5, right? K is a constant, 9 times 10 to the 9, and then the charge on B is what we're looking for, and then the charge on A, that is 5 times 10 to the minus 6, right? Divided by the square distance between them, 50 millimeters. If it is millimeters, then we have to divide it by 1,000 so that we can convert it to meters. So we have 50 divided by 1,000, and then let's not forget to square, right? And then now you can see that we have solved the conceptual physics problem. We're just doing the math. We're solving for Q of B, right? So here what we're gonna do, we're gonna cross multiply. If we cross multiply, we're gonna get 12.5 multiplied by 50 divided by 1,000 squared, being equals to 9 times 10 to the 9 multiplied by 5 times 10 to the minus 6 multiplied by the charge on B, right? So now it should be easy to see now that if we divide both sides by this term, we should get the charge on B, right? So consequently, the charge on B will be equals to 12.5 multiplied by 50 divided by 1,000, without forgetting to square, right? Everything divided by 9 times 10 to the 9 multiplied by 5 times 10 to the minus 6, and then the charge on B will be equals to 6.9444 times 10 to the minus 7 coulomb. A group of grade 12 learners want to determine an efficient conductor which can be used as the heating coil for a kettle that they're constructing for their ESCOM Expo project, right? So let's underline something here. We want to use this conductor as the heating coil for a kettle. The heating coil for a kettle. So they connected each of the 3 conductors A, B, and C in a circuit and measured the current passing through the conductor and the potential difference across the conductors. And their results are shown on the graph below, right? Clearly on the y-axis we have the current, and then on the x-axis we have the potential difference. And the first question, 8.1.1, says name any 2 variables that must be kept constant for a fair investigation, right? So the question really here is which factors affect the resistance of a conductor, right? If we keep those factors constant, then we have a fair test, right? So those factors, one of them is temperature, right? You need to keep the temperature of all the conductors the same so that it can be a fair test. If you increase the temperature, it has an effect on the resistance, so the test won't be fair anymore. Another factor you need to keep constant is the length of the conductors. If the length is not kept constant, then it's not longer a fair test anymore, because the length of a conductor actually affects the resistance, right? And then another factor you want to keep constant is the thickness. And then 8.1.2 says write down the physical quantity represented by the gradient of each graph. The gospel I've been preaching lately: if you have a graph, you should be able to derive an equation for that graph. Failure to do so, then a lot of issues are going to arise, right? We know fully well that V is equals to I multiplied by R, right? Like we said, in our graph, we have the current as the Y. So let's make I the subject of the formula. So we're going to have the voltage divided by the resistance being equals to the current, right? But then we can rewrite V divided by R, right, as 1 divided by R multiplied by V being equals to I. Clearly, we're saying that I is our Y, right? And then 1 divided by R will be our gradient, and then V will be our X, right? So now you can see that the gradient in this graph, it represents 1 divided by R, or you can simply write it in words, the inverse of the resistance. And then 8.1.3 says which one of the following conductors is efficient enough to be used as the heating coil in a kettle? Give a reason for your answer. So the key word here is heating coil, because generally we are looking for conductors that have a low resistance, right? So that we can save energy when we pass current through an appliance. But then in this case, we're looking for a conductor to use it as a heating coil in a kettle. So we need a conductor with the highest resistance, right? Because if it has the highest resistance, then it will convert more of its energy to heat, right? And then if you want a heating coil for a kettle, then that's the conductor you are looking for. So now we're going to go to a graph and try identify a conductor that has the highest resistance, right? We know fully well that the gradient is equals to 1 divided by R, right? So the conductor that has the highest resistance will have the lowest gradient, right? Because clearly in this equation, they're inversely proportional to each other. Between A, B, C, which one has the smallest gradient? Clearly, C has the smallest gradient, right? So for 8.1.3, conductor C. And then the reason for our answer, we're saying that for a heating coil in a kettle, you want a conductor with very high resistance so that it can convert more energy to heat. Now let's do 8.2. So 8.2 says that the circuit diagram below represents a combination of resistors in series and parallel. The battery has an EMF of 12 volts and an unknown internal resistance R. And before 8.2.1, we are told that when switch S is open, right, here's switch S here, the reading on the ammeter, so we have some I, which is equals to 1.5 amps, right? And then 8.2.1 says let's calculate the total resistance of the circuit, right? We have internal resistance, so we cannot just use V is equals to I multiplied by R, right? We have to use EMF is equals to the current multiplied by the external resistance plus the internal resistance. The question says let's find the total resistance of the circuit. So we're looking for R external plus internal resistance, right? We have the EMF, it is given to us, and then we have the current, right? It should be obvious what we're gonna do now. So we're going to have 12 being equals to the current 1.5 multiplied by R external plus internal resistance. So we divide in both sides by 1.5, right? So we get R external plus internal resistance being equals to 12 divided by 1.5, which is equals to 8 ohms, right? So R external plus the internal resistance is equals to 8 ohms, and that's the total resistance of our circuit. And then 8.2.2 says let's determine the internal resistance of the battery, right? We know now that R external plus the internal resistance is equals to 8 ohms. So if we can determine R external, then we're going to be able to find R internal. But how can we determine R external? We know fully well that R external is equals to the resistance in series plus the resistance in parallel, right? So now let's actually analyze our circuit. So we have a positive terminal here and we have a negative terminal here, and then the current is flowing from the positive to the negative, right? And then at this point here there won't be any current splitted, right? Because the switch is open. So the current just keeps on flowing, keeps on flowing, keeps on flowing, keeps on flowing. So basically what we have here is two resistors that are in series relative to the circuit, right? So R external will be equals to 3 plus 4, and then we're seeing that we don't have any resistors in parallel, right? So we're gonna have 0 here, and then that will just be equals to 7 ohms. So now we can say 7 plus the internal resistance is equals to 8. We're substituting R external into this equation here. So the internal resistance will be equals to 8 minus 7, which is 1 ohms, right? So the internal resistance is 1 ohms, and now we can do 8.2.3. 8.2.3 says let's determine the energy dissipated by the 3 ohm resistor in 3 minutes, right? So in order to determine the energy, so we know that the power is equals to the work divided by the change in time, right? So the work is equals to the power multiplied by the change in time. Every time when the question says let's find the energy dissipated, we're looking for the work, right? But then the power can take different forms. The power is equals to I squared multiplied by R. The power is equals to V squared divided by R. The power is equals to V multiplied by I. So depending on the variables you have, right, you use one of these equations to find the power. Clearly, for the 3 ohm resistor, we have the resistance, right, which is 3 ohm, and then we have the current, right? From the current we can calculate the voltage, right, and then use the other equations, but there's no need. So what we're gonna do here, we're gonna use this equation here because we have the variables that allows us to do so. So now the work is going to be equals to the power. In place of the power, we're going to have 1.5 for the current, right, squared multiplied by the resistance, which is 3 multiplied by the change in time, 3 minutes. But we know in physics we talk about seconds, right, not minutes. So we're going to have 3 multiplied by 60. There's 60 seconds in a minute, and then if you punch that in your calculator, you're gonna get 1215 joules, and that is the energy dissipated on that 3 ohm resistor. Now let's do 8.3. 8.3 says switch S is now closed, right? Let's go ahead and close switch S. So here's switch S here, right? And we're closing it. When we close switch S, now the current is going to split here, right, at this point. So we're going to have a proportion of the current going in this direction, and then another proportion of the current going in that direction, right? And then how will each of the following be affected? Write down only increase, decrease, or remain the same. 8.3.1, the total resistance of the circuit. The total resistance of the circuit will decrease, right? Why am I saying so? Because if the current splits here, right, then the 2 ohm resistor and the 3 ohm resistor are now in parallel with each other. So R external will actually be equals to R in series plus the resistance in parallel, right? So this is going to be 4 ohms plus Now the 3 and the 2 ohm signs in parallel with each other. So we're going to have 2 multiplied by 3 divided by 2 plus 3. And that is equals to 5.2 ohms. Clearly, this is less than the R external we had initially, right? That R external we had initially was 7 ohms. So if we close that switch, the total resistance of the circuit will go down. And 8.3.2 says, how will the reading on ammeter A be affected? If V is equals to I multiplied by R, right? And we're saying that the resistance went down, then the current should go up, right? So the reading on the ammeter will increase. If you decrease the resistance, the current goes up. And now let's do last but not least 8.4. 8.4 is saying a conducting wire of negligible resistance is now connected between points X and Y. Before we read any further, let's just go ahead and connect X and Y. So here's X, and then let's connect X to Y, right? And then it goes on to say, as shown on the diagram above, what effect will this have on the temperature of the battery? Write down only increase, decrease, or they stay the same. What effect will this have on the temperature of the battery? So if we connect X and Y, right, we have reduced the resistance. Yeah, because now the only resistor that will be getting current is the 4 ohm, right? So we have reduced the resistance. What we can see first is that R external decreases, right? So R external will decrease. But then what is the consequence of R external decreasing? If R external decreases, then IT, the total current in the circuit, increases. If the total current increases, and we know that V internal is equals to IT multiplied by small r, right? We're saying that the current increases, the internal resistance is the same, so V internal increases, right? If V internal increases, the work done by the battery will increase, and as a consequence, the temperature will also increase. AC generators at coal-fired power stations supply most of the electrical energy needed in our country. True. And then 9.1 says, state the energy conversion that takes place when this generator is in operation. So we know fully well that we have AC generators and DC generators, right? So the way I'm going to answer this question, I'm going to answer the question for an AC generator, and then also answer the question for a DC generator. So for an AC generator, the energy conversion is mechanical energy to electrical energy. And the same is true for a DC generator, right? All generators, they convert mechanical energy to electrical energy. Then all motors, they convert electrical energy to mechanical energy, right? And then 9.2 says, state one structural difference between an AC generator and a DC generator. This one is very tricky. For an AC generator, we have slip rings, right? Let me write it down. Slip rings. And then for a DC generator, we have a split ring. And then for AC, like we're saying, we have slip rings, right? So make sure you find a way to differentiate between the two. AC, slip rings, and then DC, split ring. And then 9.3, draw a sketch graph of potential difference versus time for this AC generator. Clearly label the axis and indicate Vmax on the potential difference axis. So what is an AC generator? An AC generator produces alternating current, right? But then what do we mean by alternating current? The current changes direction every half cycle, right? So if you wanna plot a potential versus time graph, then after this half cycle, you have to change the direction, right? So we go down, and then after this half cycle, we change direction again, and then so on and so on. That's what we essentially mean when we say a generator is alternating the current, right? And then on the y-axis, we will have Vmax, and then here we'll have minus Vmax, right? So this is for an AC generator. It produces alternating current. But then, like I said, we're answering for both, right? So for a DC generator, we producing a direct current, right? So after half a cycle, the current must not change the direction, right? The current only changes the direction if we have an AC generator, right? So here, if I just put this axis here and then we sketch it, after this half cycle, right, we're not changing the direction for a DC generator. We're still keeping the same direction. So on, and so on. So on the x-axis, we still have the time, and then on the y, we have the potential difference, right, and so on. So that's what you sketch when we want the potential versus time for an AC and for a DC. Now let's do 9.4. So 9.4 stories, they're saying that an electric appliance is rated 2000 watts, right? So we know that we measure power in watts. So as soon as I see 2000 watts, I'm writing P is equals to 2000 watts. And then it goes on to say that, we also have another rating, which is 230 volts, right? And then it goes on to say that the appliance is connected to an alternating current power source. Okay, and then what we are asked to do is to calculate the maximum current. So we were looking for I max, right? So here in electric circuits, we know fully well that the power is equals to the voltage multiplied by the current. But then when we're dealing with an AC generator, we have power average being equals to I RMS multiplied by V RMS. In the information that we have the power average and we have the V RMS, right? So with these two, we can find I RMS, and then from I RMS, we can then look for a way to find I max, right? So let me show you what I'm talking about. So in place of power average, we're substituting 2000, right? And then in place of IRMX, that's what we're looking for. So it remains as it is, right? And then in place of VRMS, we have 230. The conceptual physics problem solving is done now. We're just solving the math, right? We're dividing both sides by 230. So IRMS will be equals to 2000 divided by 230, which is equals to 8.6957 amps, right? So now we have the IRMS. We can go ahead and try find the IMAX, right? So what is the relationship between IRMS and IMAX? We know fully well that IRMS is equals to IMAX divided by the square root of 2, right? So in place of IRMX, we have 8.6957, right? Being equals to IMAX divided by the square root of 2. Should be obvious what you're supposed to do now. Should be obvious. So IMAX will be equals to, we cross multiplying, right? So we have that multiplied by the square root of 2, which is equals to 12.30 amps. And then 9.5 says, let's find the peak voltage. So we're looking for Vmax for the output of the generator. So what's the relationship between VRMS and Vmax, right? Very similar to IRMS and IMAX, right? So we're saying that VRMS will be equals to Vmax divided by the square root of 2. We have VRMS which is 230. Now we're looking for Vmax, right? So Vmax will be equals to 230 multiplied by the square root of 2. And then if you do that arithmetic, we get in 325.27 volts.